Hello, everyone. Thank you all for being here today, and welcome to today's session in Women in Neurosurgery event titled Artificial Intelligence and Neurosurgery Research. We're excited to have two outstanding speakers with us this evening to share their expertise on the evolving role of AI in this field. They'll provide insights on how artificial intelligence is shaping project design, data analysis, and clinical applications. They'll also discuss strategies for thoughtfully integrating AI into your own research projects. I'm Amelia Stefaniak, one of the research subcommittee representatives of the WINS Medical Student Committee, and I'm joined by my co-host, Ashley Shah Bohani, one of the events subcommittee representatives of the WINS Medical Student Committee. We'll be moderating tonight's discussion. All right, just to start things off, we invite you to join the WINS Medical Student roster and follow us on the social media platforms shown here. It's the easiest way to stay connected and hear about the exciting events we have planned for the upcoming academic year. And here's a quick overview of tonight's agenda. We'll begin with introductions of our two incredible panelists. They will then share their presentations, highlighting key applications of AI in their respective fields. We'll then move on to a discussion of preset questions, exploring challenges, opportunities, and future directions of AI in neurosurgery. After that, we'll open the floor for an audience Q&A. Please feel free to send me any questions that arise during this time and just direct them to me in the chat below. Finally, we'll close with a few remarks and announcements to wrap up the evening. So to begin, we're thrilled to introduce our first speaker, Dr. Eric Orman. Dr. Orman is an associate professor of neurosurgery and radiology at NYU Grossman School of Medicine, where he specializes in the treatment of brain and spinal tumors. He completed his medical degree at Georgetown University, residency at Icahn School of Medicine at Mount Sinai, and pursued a fellowship in machine learning at Verily Life Sciences, Google's life science research organization. During his residency, he was named to Forbes 30 Under 30 list for his work in developing prognostic models for cancer patients. Currently, he serves as the Associate Program Director of the Neurosurgery Residency Program and Director of the Health AI Research Lab at NYU. His research focuses on using machine learning to better understand the human brain and subsequently using the insights from the brain itself to advance artificial intelligence. Thank you, Dr. Orman, for being here with us tonight.
Awesome. Thank you for having me. Let me grab my slides.
Oh, sorry. I'm just going to introduce the other speaker right quick, and then we can get to your slides.
Cool.
But thank you for being prepared.
Okay.
All right. It's a pleasure to welcome our next speaker, Dr. David Dornbos III. Dr. Dornbos is an assistant professor of neurosurgery at the University of Kentucky College of Medicine, where he brings a unique blend of expertise in cerebrovascular surgery and neurointerventional radiology. He earned his medical degree from Wayne State University School of Medicine, completed residency at The Ohio State University, and went on to a fellowship in open cerebrovascular and endovascular neurosurgery at the Semmes Murphy Clinic in Memphis, Tennessee. Currently, his research focuses on AI-driven stroke workflow optimization, novel imaging modalities, and safer methods for clot removal. He has authored over 130 peer-reviewed publications and has received NIH funding to study early biologic changes in stroke patients. Thank you, Dr. Dornbos, for joining us this evening and also sharing your perspectives with us. So at this time, Dr. Orman, you're welcome to begin sharing your screen whenever you're ready.
All right. Let me this. Cool. Looks good.
Yep, looks great.
All right. Awesome. All right. I'll try to keep this 10 minutes. I have some disclosures not relevant to this talk. The title of my talk is a pun, a kind of play on words of this famous lecture by Richard Hamming. I always like to include this as an intro slide for students, maybe to kind of, I think it sums up my major feeling about why to do scientific research. It's really to know a little bit more about the world, but maybe even most importantly, a little bit more about kind of yourself. And I think that kind of sums up the ethos of my research in my lab, which I'll talk a little bit about here. Most importantly, the unexamined life is not living, to quote Socrates. So this is my research team. It's a fairly large, diverse research team. I'm actually also a professor of data science at NYU. And so we draw from really across the university. And Otto here, my corgi, is our mascot. who's actually listening in on this lecture next to me here. The my approach towards AI and neurosurgical research is really colored by my background as a mathematician and computer scientist, and focused on the fact that software scales in many cases effortlessly. And a lot of my motivation for kind of why bother to work with software in the neurosurgical domain is that it's very much the opposite of neurosurgery. Neurosurgery requires our hands, and it's really a one-on-one interaction, where software is a one-to-many. And especially, I think the opportunity nowadays is, to me, accentuated by this factoid about smartphones. The vast bulk of the world, 86%, 6.9 billion people have access to smartphones, which are state-of-the-art computing devices. And so software has the ability to really reach out and touch every single person on Earth, which is a great need. As you can see, my second statistic here, half the world doesn't have adequate access to healthcare. So the theme of my lab then is to simply either build things that help people or understand human consciousness, my second objective. And for the purpose of this talk, though, I was really going to focus on kind of the tooling and infrastructure that we use to get things done. To paraphrase another famous person, great scientists study logistics. It's Napoleon. And so I think, to me, the fundamental barrier that most individuals face when trying to do any kind of neurosurgical research, be it AI or not, is getting access to data. That's always the pain point. And the classical example a way we approach this in neurosurgery is to have medical students review charts. And one of the foundational principles of my lab and our work at NYU Langone was, how do we take the resources, the data resources of our health system, and really put these at the fingertips of neurosurgical researchers and scientists. And that gave rise to this Data Hub initiative, which really started in our department and has become an enterprise-wide initiative. And the premise behind it is this: that the enterprise, our enterprise resources in our health system, we employ computer scientists who do work for the health system, and they largely speak languages, most importantly SQL in this case, and Python and other programming languages. And we have our neurosurgeons, faculty neurosurgeons, residents, staff, and medical students who speak medicine. And there's a big communications gap. And frequently what we found was that in cases, well, either A, individuals couldn't access enterprise resources at all. They just had to go review the charts. Or even if they could somehow automate that chart review, there's a big communications barrier to being able to tell some person in hospital IT, oh, I want patients who have had information about patients who had T-lifts. You get this weird look like, what is a T-lift? So how do we bridge this gap? And so our solution, this is my chair and vice chair, who are really excited about this initiative, but our solution was to move from a model like this, where enterprise resources were routed through a centralized data core run by hospital IT, take the data core of hospital IT and graft it onto individual departments. So we suddenly had an internal data hub or data resource within our own department. And so the idea being that hospital IT then will provide the basic technology platform for this, and then the department will actually hire staff and dual train them in both understanding the language of neurosurgery, but then also those hired people will understand SQL and have access to the enterprise data resources, most notably the back end of Epic. And so this is Doug Kanzielka telling our residents that there's no more chart review, no more no data, and no more excuses for doing clinical research. And we built this. So we hired 2 full-time data scientists, Jaden and Shu, and created this infrastructure where bi-monthly there's a leadership meeting, and to review the program. The way the program works is individuals will submit a ticket on a website that we created saying that they want these things. Maybe, every patient who's had an AVM in the past 2 years, they got embolized and radiosurgery. And then that will then create a work ticket, which we use as GitHub as for our ticketing system. That will then get handed off to one of the analysts who will then look through it. And at this point, they both know neurosurgery well enough that I can tell them that exactly what I just said. AVMs that had radiosurgery and embolization in the past 2 years, and they can directly translate that into a SQL query, recover all of the charts of those patients, and then go to whoever asked for it and clarify, like, hey, did you want to know, what were their outcomes? Did you want to know what the doses that they got for radiosurgery were? And then the data scientists will provide an Excel spreadsheet to whoever requested that, and that entire process takes 2 weeks. No chart review. So to me, this is the most important thing that kind of we've built or done, is by making the data resources of the health system and really putting it at the fingertips of our department members. This is also free. We pay for it out of the departmental budget. Um, the second maybe kind of precursor to actually doing research is having computers to do it with. Uh, we've built a large computing platform. Most of this is hand designed by me, um, but providing a lot of compute nodes with GPU computing to do deep learning research and deep learning with. Language models are very much kind of the hot thing. And one of our goals at NYU was to take these state-of-the-art language models, GPT-4, DeepSeek, and what have you, and again, find a way of getting them direct access to the same data resource in a way that's compliant with regulations, HIPAA, and so forth, and institutional security policies. Noting that if we can have the AI read all the charts, we don't have to do it as clinicians or as students in many cases. We'll skip that. So language models, I'm not going to belabor the slide in the interest of time, but there's many different kinds. Most of you are familiar with ChatGPT, which is the most famous one. So the question is, how do we get this deployed in a way that's compliant? So AI can read the charts, so we don't have to. There's two ways of doing this. One, you can use that compute platform I showed off before and host the models yourselves, which we do. There's some advantages to self-hosting, mostly on cost, that if you self-host is relatively cheap compared to using ChatGPT. You can also, again, at an enterprise level, contract with OpenAI or Microsoft to have a HIPAA compliant version of these tools that you can then send data to, have ChatGPT read through whatever you're doing, get results back, and it's done in a way that's compliant with HIPAA and other security regulations. We run this platform as well. So again, no chart review, but then also massive AI models that can be used for predictive work. And there's again how we host it. There's a kind of a chat user interface if you want to chat with it like ChatGPT. There's also a REST API for programmatic calls. Last but not least, I have to give a plug. There's a CNS chatbot. If you haven't used it, it indexes into Claude as well as all the great CNS content. And as a member of the CNS, you have a state-of-the-art language model at your fingertips as part of your membership. So the why this is exciting and why LLMs can do this is really maybe calling it as fuel for research. Being able to access data and have language models plow through all of it for you can set you up to do a lot of clinical research at very low effort. All you really need is an idea and a minimal grasp of programming. So one of the things that we did recently was have it read through the scientific literature, kind of have a review papers more or less write themselves. And you can see here we benchmarked the ability of the models to choose the appropriate citations. They're about 98% accurate. Also used to put together some very large cohorts for clinical research. One is NYU Mets. This is actually published in Nature Communications, but it's one of the world's largest data set of MRI imaging. It's about 14,000 MRI scans from 1,400 patients. It's the longitudinal scans, and this is kind of a good example of what we can do. We had the language model read through all the charts of our brain met patients, generate large tables describing their clinical outcomes and what they were treated with. And then we took all the imaging of the brain mets patients plus these tables, and we put it on the internet for other people to access after de-identifying everything. As part of really our commitment to open science and find some way of taking these tools, doing something really cool, and then making it available to the community. NYU Q&A is another large data set, again, curated with language models. It's 10 million text messages from patients to their providers. It's not just neurosurgery, but it's the world's largest non-commercial text message data set. And we use to study the communications of patients with physicians. I think neurosurgery is an interesting subset here. Obviously, we have people who have neurologic injuries and it changes their communication, especially their prosody. And that's something that we've been studying with this data set. Another one's the thoracal. It's the world's largest data set of thoracic imaging. It's over 10 million chest x-rays, 1 million chest CTs, and 11 million free text reports. And we're using this as part of a research project to study the reconstruction of three-dimensional imaging from two-dimensional imaging. So maybe in conclusion, it's not really about computers, it's about patients and patient care and what we do with it. And I think to me, the most exciting things are, I think with a little bit of institutional buy-in, it's possible to have AI do chart review for us, which can enable a phenomenal amount of downstream research. And to me, I thought that would be the most important thing to talk about here, since I think the biggest barrier to people doing AI research isn't AI at all, it's access to data. This is my team. takes a big crew to do AI research, and maybe afterwards in the questions can talk actually about AI research if people are interested.
Yeah, of course. Thank you so much for such a fascinating presentation. It's definitely exciting to hear these fresh perspectives on the field and I believe it really spoke to some of the core aspects, the current limitations that are um, the AI poses to medicine in general and the opportunities it also brings. Hopefully, we'll have a chance to circle back to some of these themes during our panel discussion. For now, we'll transition to our next speaker, Dr. Dorbos, to continue exploring the diverse ways that AI is shaping neurosurgery medicine in general. At this time, you're also welcome to begin sharing your screen.
Perfect. Give me a second just to get into presenter mode. All right, there we go. So I certainly could have used some of that for some of the projects that I'm going to be talking about here in this next part. I'm going to kind of pivot into less how do we build it and more how do we use it and apply some of the commercial stuff that's already out there and in existence. And we'll kind of walk through some of the different ways that we've used this here at UK and where I did my fellowship down in Memphis. These are my disclosures. None are relevant to this today. So I'm a cerebrovascular neurosurgeon, so I focus both open and endovascular, and it encompasses a lot. And AI has already touched a lot of different areas in this space. There are um, a number of AI platforms for stroke, aneurysms. Now, carotid disease is kind of a newer one, and intracranial hemorrhage. And it's only a matter of time before it touches the other areas as well. Now, the AI influence in the CV space, and as I go through, especially the ischemic stroke and the aneurysm, different AI models and programs that are out there and are currently in use, they're largely helpful for detection, triage, and then treatment and kind of guiding treatment decision making as well. It's probably it helps with all three. We'll talk about this a little bit more in the panel discussion later, but AI has really helped in the detection side of things, and we'll kind of talk through how we've used that to build our stroke program here in Kentucky. So for detection, there's two primary programs and companies, industry partners that are out there and are using this. We at University of Kentucky have used Viz AI over the past, it's been about 7, 8 years now. Rapid AI is another very good AI platform that's out there. They both work to detect when you have a large vessel occlusion in an ischemic stroke patient to try and identify patients that would benefit from thrombectomy early on in their care. So this was a study I did while I was in my fellowships. This is about 4 years ago. But really just looking at the impact that Viz had on our stroke system down in Memphis. So the first thing that we did was we looked at the first 700 strokes that had come in over a 6-month period after Viz had been implemented at both the hub, and there are about 4 different spokes at that time that were also feeding into this. And we kind of broke down the patients that where the AI did accurately detect. We broke down the patients where it inaccurately detected an elbow, and we compared all of that to some historical controls as well, just to compare it to the standard of care. What we found is kind of what you would want to see with a AI platform that's trying to identify really the things that you can't miss. We found a very high specificity and a very high negative predictive value in that cohort. So really, the model doesn't miss. It very rarely is going to not catch an elbow that happens. Now, the sensitivity and the positive predictive value were quite poor. Which is just because the system is designed to not miss anything, and it's relying on the human complement to that to screen out the ones where it falsely alerts for these things popping up. There's definitely room for improvement there. There is absolutely a boy who cried wolf problem when you are overcalling everything. and you have too many false positives. But this is at least a great start in terms of what you're looking for. So looking at how this actually also impacted our metrics, because before this, we were relying on waiting for the scan to be read by a radiologist, and the radiologist alerts the ER, and the ER alerts the neurosurgeon. And there's just a lot of steps that have to happen. So what we found was that implementing the algorithm and using this system across those four spokes in the primary hub led to a 23-minute drop in the time at which the large vessel occlusion was identified and relayed onto the ER to start the triage process for that patient. That impacted not only obviously just that notification time, but impacted when the patient arrived until they got onto the table and how quickly they were getting blood flow back again. Now, translating this up to where I'm at now in Kentucky, we are probably not the buckle of the stroke belt, but we are right in the middle of the heart of it. They happen all the time here. So we've used Viz here. We have a central hub, and we actually now have a 45 hospital network system that all feeds into this system. So it's a lot of scans and a lot of patients, but the using Viz AI has really helped us to take a lot of outlying hospitals and some places that are up to 8-hour drive away from us and funnel them into a centralized system that's able to help screen for these particular patients. In addition to just the fact that we are now capturing 45 other hospitals in our stroke network, one of the nice things, and this really is less to do with AI and more with how you can leverage this platform to grow your referral base, but the triage and the interhospital communication platforms are phenomenal. In addition to the AI, the detection, and the alerts that you get, the ability for us to interact and text back and forth to the outside hospital ER with our nurse coordinators here really improves just the overall triage of these patients. I mean, here you can see over the course of about 15 minutes, we identified there was a large vessel occlusion. We got an exam. We found out whether or not they were going to give TPA and had the patient blood pressure goals and transfer already set up. The other nice part, and especially when you're working with outside hospitals, is being able to give feedback. You have these same people on the line once this patient gets up to you, and you can open up that carotid artery and you can open up the brain. And giving them the pre and the post imaging really helps to build the team. And by team, I mean not just the people at your hospital, but the outside hospital folks that are referring to you and that you're working with. We have used this in kind of two ways. It's not just increased our speed, it's also significantly improved the success of the transfers. And by success, I mean not accepting a whole lot of patients that don't need to come to UK. One problem we have in our hospital system is we're always packed, we're always busy, we're always operating at 90 to 95% capacity. So keeping patients out of UK that don't need to be there, that don't need a procedure and can stay at their local hospital has been really, really helpful. Over those 2 years, 7% of patients transferred and around 10,000 patients were able to stay at the hospital that they were at because they could get the level of care that they needed there. This is looking at the transfer patients, and you can see for patients transferred into UK before Viz, when we were relying on radiology reads, it took about 55 minutes between when the patient came to the hospital and then when the images actually interpreted by a radiologist. With the implementation of the AI, it dropped all the way to 17 minutes, which is a massive reduction in time for these types of patients. We saw something similar with our hub as well. It not only led to improvement in imaging interpretation times, but it was faster access, it was faster revascularization, all of which is saving brain in the setting of stroke. In addition to that, it increased our thrombectomy volume substantially. I mean, some of this here is over the course of the 32 months before and after we implemented Viz, there were increased indications for the types of patients that were needing a thrombectomy. But you can see there we had a near twofold increase after we used this AI platform to ease the transfer process. And that's only increased. Over the last 24 months, we're on track for over 550 thrombectomies. So it's just continued to kind of feed into the system and get these patients to where they need to go. I'll kind of pivot into aneurysms. In here, I'm going to talk a little bit more about rapid AI, just to play nice in the sandbox, since they have a very nice platform as well. But with aneurysms, what we're really trying to do is just not miss any. And there are a good number of aneurysms that either get missed or are just hard to detect in a quick manner, and to get to the patient or get to the providers that they need to get to. But rapid AI, this is a study that was done up at Stony Brook a couple or actually no, just a year ago, and they found that the use of this AI algorithm led to a specificity of 97.8%. And also importantly, the sensitivity was nearly to 90%. So this algorithm, this AI platform is really not missing aneurysms, or at least not to a significant degree. What they also subsequently found was that the main area where the AI does miss aneurysms is in aneurysms that are less than 3 millimeters, which really is pretty clinically insignificant of an aneurysm. If you have a 2 or 1 millimeter aneurysm, that's never going to get treated. They just don't need to be treated. They did find that comparing the ones that were missed, you can see here, radiology, this where is the human error kind of comes into play, was missing more aneurysms that are starting to get up into clinically important and treatable pathologies. I mean, you're up here in 5, 6, 7 millimeters, and the AI is missing significantly less aneurysms than your standard of care with radiology. The other thing that really has impacted this space a lot is surveillance of aneurysms. So, as I just said, a lot of aneurysms just don't need to be treated because of their size, but they do need to be watched. One of the issues with watching aneurysms is our inability to really measure the entire volume and size of the aneurysm. So this was a study that was done by Goodman Campbell up at Indiana. It was a single center aneurysm series of 5,000 patients, and they found 5 patients where they had interval imaging, a CTA, and another year or two a CTA, and then after that, the patient had a subarachnoid hemorrhage. And none of those patients were treated. And from the quick neurointerventionalist or neurosurgery read was roughly stable on those images. What they found was that the maximum dimension, which is how we typically measure aneurysms, at least by just as a human, the increase was only about 1.8%. If you can measure the volume, which is very hard to do with a two-dimensional tracing, the volume actually will increase by 6% in these aneurysms that ruptured. So volume is a much more sensitive test to aneurysm growth than maximum dimension was. When they start, and that's largely because aneurysms they're not perfectly spherical things. They're very irregular, kind of multilobulated. And what they found was that utilizing the rapid AI software was actually able to measure the increase in volume. That largely, if you compare, this is the pre is the blue and the post is kind of the darker blue purple. That if you're just looking at it with your naked eye, really does, if you put two side by side, it's hard to actually tell which one is bigger, which one's different. When you actually can overlay the volumes on top of each other like this, makes it much more just you are much more able, or actually you're not, the AI is, to detect the aneurysm growth, whereas the human eye and human measurements really can't. And then this is kind of getting into simulation, which is actually getting out of AI a little bit, but this has really started to take over how we size stents. So Sim Size is it's been around for a few years now, but it's a software algorithm that's designed to help you take a 3D rendering of the artery and the aneurysm that you're treating, and is able to predict with very good accuracy where that stent is going to land as you're unsheathing it and laying it out. And it's highly accurate, which really decreases the number of devices you need to potentially open. It improves the safety profile of these things. And there was a study that was kind of recently done that also showed that there was a significant decrease in the treatment duration and radiation dose when this system was used. And this is kind of what you're looking at here is with Simmons size compared to without, you have about a 8 minute decrease in duration of the procedure, and about a 30% decrease in the overall radiation dose. And you're able to use a smaller stent, which is just good from a safety standpoint because you have less metal inside the aneurysm. They did the same study with the web device and kind of found the exact same thing. It significantly decreases the treatment size, it decreases the radiation dose, and all of this is built on a simulation AI platform to really improve the predictability of where these things are going to land, to improve your ability to size these things for treatment. And then this is just another study that we've recently done as I'm starting to dabble, not nearly as much as Eric, but starting to dabble into the machine learning space. But we took patients, we were trying to predict who would develop enough malignant or severe enough malignant cerebral edema that they would require a hemicraniectomy. And it's not always clear in the first 24 to 48 hours who's going to need it and who's not. We do know that if you get the bone off, if you could do that decompression within 48 hours, you do have a significant improvement in patient outcomes and decreased mortality. But the goal here was really to help us predict which patients are going to need it and not administer the surgery to patients that won't. So we took around 500 different patients. We plugged in their pre-procedural head CT and their 24-hour head CT in addition to a number of demographics. And we just recently actually able to build a model that's able to pretty accurately predict which patients are going to develop malignant cerebral edema. We're just about to start a prospective study to kind of see how well this actually does with a prospective cohort of patients. And then for next horizons, there's a lot coming down the pike, especially in the cerebrovascular space. But endovascular robotics is coming very quickly, and a lot of it is using AI to guide the robots in the systems that we're using. I think you'll definitely see more refined detection tools, not only for stroke and ICH, but also for aneurysms, for carotid disease. And really the streamlining of workflows, not only how we've used it, but there are a number of companies now that are starting direct automated referrals where if you have a CTA that's done within your network and there's an aneurysm detected, the computer is already referring that patient to a neurointerventionalist within the network before it's even read by a radiologist. And then I guess some future cautions. I think we'll get a little bit more into this here in the next phase, but the bias is, I think I'm going to save this for the discussion part, but we do have to be careful as we kind of bring in more and more data. The patients that we're plugging into it, if we're treating a diverse population of patients, which we are, the data going into these systems also needs to be diverse and needs to account for some of that variability. So I'm going to save some of that for the actual panel discussion. And before I hang up, I want to make sure everybody knows and is ready as we are gearing up for CNS actually just in a couple of weeks. So if you're not coming, make new plans. I'd love to have you out there.
Great. Thank you so much, Dr. Dornbos, for sharing such a compelling look at how AI is streamlining stroke detection and workflows already. It's really exciting to see how it's already enhancing patient care in this realm. I think both of the talks tonight really speak to the breadth of AI's potential and where new opportunities may be arising in the near future. So at this time, we're now going to shift into our discussion segment of the night. Ashleisha will now lead us through the remainder of tonight's event. Please continue to send me any questions you may have so I can populate them in the Q&A portion. Thank you.
Thank you, Dr. Arman and Dr. Dornwitz, again for sharing your insights. We'll be moving into the Q&A portion. Okay, so we'll start the discussion with a question that's especially relevant for students who are curious about getting involved in AI research, but may not have a technical background. To start off our discussion, I'd like to ask our speakers, for medical students who want to begin exploring AI in their own research, but lack a computer science background, what initial skills do you suggest learning to give the greatest return on effort?
I think the single most impactful thing you can learn, maybe period, is a general purpose programming language. So to me, that'd be standard part of the medical school curriculum. And I think when in doubt, I think your best bet is going to be Python. Python's it's dynamically typed, it's highly readable, and it's very, very expressive. If you write it functionally, object oriented, like it's very, very, very straightforward to work with. It's also the language of AI. And so I think when in doubt, learn Python. Your second best bet is going to be JavaScript. It's the language of the internet. Everything's on the internet. And so I think that would be the single most impactful thing you can do. Maybe my second one would be obviously, and I think the thing about general purpose programming is you don't need to just use them for science. You can use them to do other stuff. When I was a resident, when I was the senior junior, our call schedule was made by a software program that I wrote. I was like, I don't want to deal with it. Computer will figure it out. Like you can do those sorts of things with general purpose programming languages. My second one would obviously be like statistics. If you want to do science with AI, knowing statistics and just the scientific method in general, like being able to phrase a good hypothesis based on the literature and test it rigorously, it's a must for doing any kind of research.
Yeah, I would definitely second the statistics piece. It's the I and I mean, I was definitely gonna let Eric lead that one off because I have a, let's call it a superficial understanding of AI machine learning. But what I would say is a couple things. One, definitely statistics is the more you can learn there, that doesn't just go into AI. That's kind of research in general. And even if you're not going to go into academics and be a hardcore researcher, if you just want to be a clinical neurosurgeon, understanding statistics and being able to interpret new
Well,
papers and new data that comes out is incredibly important. And it's a very underappreciated skill, I think, amongst medical students. So and even my residents, we had that discussion yesterday about just kind of when you are going to interpret what a paper is telling you, being able to understand the statistics that were done and how that actually informs what you can get out of it is huge. The what I've really done actually in my lab is getting good collaborators. We have a very strong bioinformatics group here that's very collaborative. I didn't talk about it today, but one of my main research projects is looking at perfusion imaging in stroke patients, and then we're also grabbing intracranial blood samples and we're identifying where within the perfusion map these blood samples are coming from. With these blood samples, we're looking at proteomics, we're looking at platelet biology, we're looking at arterial blood gas analysis, we're looking at EV, and we're looking at a lot of different metrics. And each individual patient has, between the imaging and the clinical data and then all the biologic data that we're pulling out, there is a good 600 variables per patient, which is way too much for me to sit here and just kind of glean through. We just recently started bringing in some machine learning, and hopefully eventually we're going to move into some imaging analysis for like a CNN down the road. That's all outside of my scope and honestly what I'm going to be able to pull off over the next couple of years. But bringing in really good collaborators, I think, is very key and very helpful as well.
Awesome. Well, thank you for both of your insights. It sounds like JavaScript, Python, and biostatistics are very high yield topics to look over for medical students. So building on those ideas about how students can start developing the right skills, let's turn to where those skills might make the biggest difference in patient care. For our next question, I would like to ask the speakers, where do you see the most immediate opportunity for AI to meaningfully improve care for neurosurgery patients?
I think a big piece is going to be outcome prediction to inform the surgery that you're going to move into. It's kind of where I see a lot of the newer AI models and just the newer data coming out that seems to be moving in that direction. And I could easily see that making a big impact, especially in spine surgery, where you've got multiple different ways that you can approach a pathology. And the more you can bring in AI to inform your outcome, the better off you're going to be. It definitely, from a stroke and aneurysm standpoint, kind of like what I was talking about, I want to say it's maxed out, but it's we're starting to get into diminishing returns in terms of at least like the early detection and triage. There's definitely improvement that can be made in the AI's ability because a lot of what's been helpful from both Viz and Rapid and some of the other software companies is their software is really good. Their AI needs some work. The detection is just it's okay, but it really is, it misses so much that you end up doing a lot of it on your own as the clinician. The software and platform is really helpful from a triage standpoint, but the AI still needs some work. So there's definitely refinement that needs to happen there. But that's kind of where expect it to continue to mesh and to mold.
I guess we're kind of in a similar vein of thought here. Rather than outcome prediction, though, my answer was going to be just outcome measurement. I think the single first on a broad point, I usually don't think about AI in neurosurgery since to me, as a computer scientist, I think about things that scale, and like neurosurgery is a relatively small discipline compared to like internal medicine. Um, but to me, like in all the clinical neurosciences, the biggest bottleneck to everything from how we take care of our patients to how we develop drugs or how we assess our treatments, like thrombectomy, is actually just measuring the outcomes. Like to assess neurologic function requires a highly trained person to, again, one-on-one interact with the patient. And like that's the complete opposite of scalability. So I think finding outcome measures using AI that can automate some of that task or surrogate measures for those outcomes, which will let us better scale neurologic assessment is probably the single greatest area of impact.
Yeah, I like that a lot actually, because there's some really interesting stuff that's coming out where you can, I mean, honestly, I expect AI to do a better job of identifying, especially cognitive outcome data after a stroke, after a ruptured aneurysm, than we can. It's that's one thing we've actually been working on within my lab is identifying better markers of cognitive outcomes. Because then, at least for cerebrovascular, we often will use modified Rankin score, which is not, I mean, it's very easy, but it misses a ton of the granularity of like what the patient's actually experiencing and undergoing. So we've been working on a couple of different cognitive assessments, but the one of the issues that you run into, and this is somewhere where a computer could definitely help, is the more in-depth your cognitive assessment score gets, the more of a drain, the bigger drain it is on your staff that have to actually administer that thing. So you're taking a ton of manpower to get a still better but not great cognitive assessment. Yeah, I would love to see something like that where you actually have a computer or a system that can actually more accurately figure out where that patient's actually at would be awesome.
Totally. Like we could automate the mocha or like
Yeah.
to the point where you could like every hour get a mocha. That'd be amazing. That'd be such groundbreaking. So yeah, to
Mhm.
me, that's what I'm most excited about. Someone needs to do that.
Yeah, I like it.
Thank you both for your great discussion on this question. Sounds like outcome prediction and outcome measures are where AI has the biggest impact to make here in neurosurgery. For time's sake, we're going to skip over question 3 for now and move on to the audience Q&A portion of this. So thank you to everyone who's already submitted questions in the chat or through the registrations form. Please